Hey, welcome back to the lab. We have got an awesome video for you today. We are going to achieve a kilowatt. Okay? 1 kilowatt. I'm not going to stop until we get a kilowatt. So basically what we've been doing is we've been tuning the gate drive on the battery module, and I'm pretty confident we've got that. I'm pretty confident we've got that like 90% tuned. Oh, wait. Before we dive in, I've got a secondary objective for this video because there was one comment that just about killed me. I was on the floor laughing when I read this, and not in a mocking way, in a I completely understand sort of way. So there was someone who reached out in the comments. I can't remember your username, but I just want to say you are awesome. I love that you left this comment, and in fact I love all of you. There's so many of you that keep me so honest. I love it. Anyways, so I don't know if any of you guys work as an engineer, but if you do, you might have this guy at the office, and there's a couple guys at my office that, man, they just have so much wisdom and so much knowledge, and they have seen lots and lots of designs that work and lots of designs that didn't work. And you know, sometimes it feels like they've got so much experience. It's like, how would I ever understand as much about electronics as they do, right? And yeah, this is a little bit of water cooler talk. Hopefully, whatever. Skip ahead like a minute if you don't want to hear this. Anyways, so these guys at work, and like, man, I really look up to them a lot. And I don't know, I can't really do it. They've got like, you know, the deep gravelly voice, and then and for some reason, I imagine that you're that guy at your work, wherever it is that you work. And he's like, what are you doing? You're just plugging daughter cards into 250 volts and things are blowing. Like, why aren't you being more careful? It's like, why are you being so reckless? Oh, I don't remember the exact words, but that's basically the gist of it. It's like, don't you understand that this isn't how it's supposed to work? And yes I do. But it's not very exciting or interesting when you're doing it the right way. So usually I skip over all those boring bits where I'm actually testing the design and making sure that it works before we film an episode. Normally I just kind of jump right over that and get right into it. So I'm going to take a step back and try to show you guys the right way, try to show you some of the other steps. The other thing, the other half was, the way that I read it was, don't you know how to use an oscilloscope? You can't see the waveforms that you're talking about from what I could see. And yeah, so that's a problem with ultrascope. That's like the Rigol tool to let me do direct capture of what the scope sees. What I'm seeing on the display of my scope is not the same as what's being captured. Because if I tweak any of the knobs on the scope, it doesn't push that back to ultrascope. So it's like a one-way street. So ultrascope gets whatever data it gets from the scope. And if I adjust something in ultrascope, it adjusts it on the scope. But if I adjust it on the scope, it doesn't. So basically what happens is I set up the capture. Sometimes I get into it and I start tweaking the knobs right to make the display show me what I need it to show me. This is something that we did because a while back. We had a camera on the scope, and it was usually a little out of focus, and usually had some glare, and it was kind of hard to see, so we went for the direct data capture, which is awesome. But sometimes when I'm really in the moment, I start fiddling with the knobs on the scope, and then what you're seeing in the scope capture just doesn't make a whole lot of sense, and that's unfortunate. So, at any rate, I really appreciate your experience. I'm so glad that you're here. And quite honestly, I need some guys in the shop keeping me honest, because if I start skipping too many steps and I start being a little too brief and I start, hiding some of the nuanced work that we're doing to actually make the design work, some other folks might be a little misled. They might not understand and they might rush into something and, just want to set a good example. Speaking of good examples, ignore the way that I'm ground bonding this prototype. It is super not up to code, but that's because I'm not installing it, right? This isn't going to have 20 amp volt currents. I'm applying earth ground through this anemic cable that's way too long to a ground stud that goes through the chassis and back out. Ignore that. Anyways, let's dive in. Time to quit sipping the coffee. Time to quit chatting. Time to get down to business. So where are we going to start? Here's what I want to show you. So what we've got is we're doing, well, what we're doing is we're dialing in the gate drive for this daughter card. And we're doing that by applying 24 volts to the UPS. So that's powering all the low voltage circuitry. And then I'm using the electronic load using the lab power supply to apply voltage to the DC bus. So basically we're applying 32 volts to the DC bus, and I'm going to enable the inverter, and then we're going to take a look at what that looks like on the scope. And just looking at what's coming through, so I added all the ground leads because there's some ringing and some noise in the measurement that didn't look very good. And what you're seeing now in the scope capture, that actually looks a lot better through ultrascope than it does on what, because I'm seeing all the glitch, because right, this is a sine wave, so the duty cycle's doing this and my scope is not keeping up. But the ultrascope captures just like a sequence of images almost, like, that's kind of nice. So what I'm seeing is channel 1 and 2, which is these upper two gates, it actually looks pretty good. You see like that weird kind of like plateau in the gate drive waveform, and what that is we're turning off the upper FET, and we turn it off so fast, and it sits there and waits until the low side FET turns on, and then that brings the bus down to zero. So basically, we've got the little capacitive, the bootstrap cap that's driving the gate, turn that on, turn it off, and then the low side FET kicks on and drags the output voltage down. There's that time where we're just kind of floating, we're just kind of hanging in limbo. And that's okay, right? Because I think we need margin there. Because when we're up at 180 volts, 200 volts, I think we're going to need some margin. I think that there's going to be some problems where it's going to take longer to turn some of those on or off, and we're going to need that extra timing margin, and that's what we're going to kind of get into today, right? We're going to ramp up the bus voltage, look at how the gate drive waveform changes, and as we're doing that, hopefully we'll get this to a place that's more optimized. We were dissipating about, well, quite a lot of power in this particular region right here. I think something about the gate drive just wasn't great. There's a little more ringing than I would like, right? We're at 50 volts per division. We might be violating VGS. We really, really might be. Unless that ringing is actually the source and we're just following it around, that'd be a good thing to verify. But based on what I know, I think that's bad. And we're going to need to add a gate drive resistor bigger than 0 ohms, which is not surprising, but we're going to need to add a bigger gate drive resistor to reduce that ringing. So let's see, that's channel 4. It's right there. If we want to clip onto, hey, no, that's not too bad. Okay, so since the blue channel is following, so channel 2 is following channel 3, so that means there's just some ringing on that switch node, and the bootstrap cap is following it around. Interesting. So it's not a problem with our gate drive. That's just, woo, having some fun. Woo, boy. Yeah, so our gate drive is following. Yikes. Oh, it still makes me a little uncomfortable. Yeah. One of those is bouncing all over the place. Why? What is different between these two? They should both have the snubber. Well, dang. Alright, so we might be fine. It's certainly not great, but yikes. Okay, so I guess what I want to do is I want to crank up the voltage a little bit. Okay, so what I just saw, right, so I don't know, for those familiar with power supplies, you might be familiar, but you can get some ringing on the gate, and that can lead to transient overvoltages where you're violating the gate to source voltage of the FET. If you violate that, even for a moment, it can break down internally and then cause it to fail short. That's what I thought may have been happening sometimes. And so we've got a couple intermediate steps that we can go to. The first one that I would like to go to, though I can't really, would be about 50 volts, and that would be plugging our batteries directly in, and that just scares me because of how much current these can provide. So what I'm going to do instead is I'm going to modify the battery daughter card to output a much lower output voltage. We're at like 180 volts right now. I'm going to set it to like less than that, like 60, like 80, like a very small voltage, and then we're going to see how that looks. We've got the mains output, we've got our earth connection, we've got the gate drive monitor going on over here, and we're going to power it from this power supply. Hey, there we go. That's a sine wave. And what are we seeing? Lots of ringing on that one note again. The other one's looking fine. Cool. Dope. Oh, that's a shame. So now on the upper collection of traces, what we're going to see is the switch node and the 2 gate drive signals. Yep, so you can see the switch node. Okay, I can see it. Wait a moment to refresh. There it is. The switch node is ringing and the gate is ringing right along with it. We are not violating VGS. That looks pretty good. That looks pretty good. Yeah, is our micro going out to lunch? It's alright though. Alright, what are we seeing? Actually, less ringing. That is weird. Less ringing at the higher voltage. Somebody said for that. Looks like we've got a lot of dead time, so that's really good. Plenty of dead time. That's just the main micro going out to lunch again. So speaking of, I did a little bit of debug on that. There is definitely noise coupling in. I think there's something to do with the split planes, because I think there's a split power plane referenced to the 1.8 volt local regulation. So we might be getting some capacitively coupled noise from some nearby supplies, and that's really a shame. If I had more ground layers, or I limited this to a 4-layer board, that might have been a little unwise. Maybe I should have just let it be 6 or 8 layers. And that would have made the layout a lot more ideal. I think I might have cheaped out a little bit too much on this one. Might have pushed it a little too far. 180, all right. Let's check out that gate drive. Pulling an amp from the electronic load. Whoa. Something's going weird. The scope lost its connection to my PC. Hopefully we weren't shoving a bunch of current through ground. Clean reboot. Okay, that gate drive is looking good. There we go. Pull the plug. I'm just going to inspect that waveform, and just a teensy bit marginal. Actually, that's not half bad. So specifically, this part of the waveform. Oh man, human tripod. There we go. Specifically, that part of the waveform is what I'm seeing. A lot of ringing. For the most part, it looks like we're handling that just fine. But notice now how the slope, that blue slope,
it doesn't look like a sharp transition like it used to. It looks kind of sloppy. And that's what makes me think we might be shooting through. Right before it was really snapping from one to the other. And we're pumping like 4 amps of gate drive into that thing. I'm going to bring the voltage back down a smidge and just look at how that switch node looks. Something doesn't sit right with me about that. Yeah, you can see it's very similar. Same volts per division. If I'm feeling ambitious, I'll put them side by side. Yeah.
Here we go. Okay, so we're getting 1.5 amps in, 32 volts, so we're pulling about 40 watts. Oh boy. That was not good. Yikes. Okay, the UPS just reboot. Watchdog must have got it. I think we survived. Oh, that was scary. My adrenaline's going. Okay, gonna see if I can get a good capture on the scope. Before we do, these FETs are nice and cool. How are the other FETs doing? This heatsink's pretty warm. The inverter heatsink is pretty warm. We're gonna try that again. Yikes, that got real angry real fast. No! We lost the scope capture. We lost the scope capture. No! Come on. Whew. I'm not gonna lie. The scope looks like it was really struggling to capture that. Okay, rebooted. DC bus is nice and low. Heatsink is nice and it's warm to the touch, it's not hot. It's about 20 C, something like that. Got AC volts now. Okay, gonna try that one more time. Wow, that sounds angry. Whew. If that isn't anxiety inducing, I don't know what is. Whew. That's got chills running down my spine and makes me want to plug my ears because whoo, that did not sound happy. Okay, I just want to show you what we're seeing on the scope. It actually looks pretty good. So we're here at, what's that, 50 nanoseconds per division. The switch node is coming up really fast. We're getting some switching losses. We're burning a few watts in those FETs. But it looks like we might be able to do it enough to the point where I think I might be okay with switching to the batteries. Though that scares me to no end. I think we can do that based on the waveforms I'm seeing, right? I'm not seeing any shoot through. It looks like our dead time has lots and lots of margin. We've been stepping up the voltage. It still seems to be behaving pretty well. Power is applied. We are plugged in. Scope is ready. That ain't right. Okay. That's not what's supposed to happen. That didn't look like a sine wave at all. That was bad. We don't... Somehow, some way, we saw a short on the output. You were there. Shouldn't be this fuse. It was! We blew the fuse. We blew a 10 amp fuse with a 2 amp current limited supply. That is mighty impressive. Must have just had a weak fuse. Okay. I did a little bit of cleaning up. Never do that. Let's try that again. So we must have had some kind of event that involved a lot of surge current. There we go. So rather than using our trusty scope, since it seems as though that was super not a good idea, let's try the DMM in AC mode. And let's see what we measure and the output. You can see that fairly well. 0 volts is what we're reading. It's powered on. Before we do that, quick spot check. Let's make sure we didn't get a short on the DC link. Looks like we're good. Looks like we're good. Volts. DC, that's where we're going. Volts DC. All right, gentlemen and ladies. All right, folks. Let's see what happens. What was that? Is that the fuse again? That's obnoxious. I heard a little pop. It almost sounded like a fuse. How do we keep blowing a 10 amp fuse? I was looking at the input current. It was 3. Maybe that is just a 1.0. I mean, I guess comparing it to the 7 amp fuse, it does almost look smaller. Oh, whatever. Let's put in a 15 amp fuse. 15, not 50. Because that was fine. It was like super duper fine. Okay, see it up there. No voltage. 2.5 volts AC. I'm sorry, what? Wait, the main micro is not resetting. That's cool. Let's try that one more time. Right on, right on. We have the two daughter cards aligned. They are installed in adjacent slots. We're going to power it up and see what we see. So, we're going to go for broke here. Neutral. Yep. Plugging it in. Ohm checker. Looks fine to me. Baby, UPS, please. Just turn on this once. No. We're gonna power it on. We've got the two cards installed right next to one another. Nice little power electronics sandwich. Now, with the power supply kicked in, we now are able to turn on the system. And what I'm going to be looking for is, does the high voltage bus turn on and stay on? It does. Great. We're pulling about 0.6 amps. Cool. 0.6 amps. That is not a lot. That is a reasonable amount of current. Yes, that is good. Now the real question is, can we get the scope on it without blowing the thing up? I'm hoping for a yes. I am hoping for a yes. We've got line. We've got neutral. We've got it hooked up to the scope. This is pretty much a no-load test. Doesn't get much easier than this, folks. We'll see. Might be catastrophic. Might be fine. Alright. Plug your ears. It's time to check. That sine wave looks disgusting. It did it again! It did it again. We were at 0.6 amps, then all of a sudden, short circuit. I'm loving the battery daughter card for what it's worth. I think it's doing a great job. Keeps surviving all these shorts downstream. Let me guess, it failed in exactly the same way. I concede we can't operate at 250 volts right now. Okay, I give in. All I want to see is back to where we were, right? I'm not asking for a whole lot. All I want to see is a sine wave that looks vaguely sinusoidal. Doesn't even have to be great. It just, you know, one of them. Just one, maybe. Alright, we took the bus back down to 185. Should be making 120 volts RMS. It just looks like garbage. What is that? What? Why? Why does that sine wave look like trash? Okay. Here's what I'm gonna do. I'm gonna hook this up the way we had it hooked up before. So we got it wired up in a way where it should work. Should be 120 volts RMS. Plugging the kilowatt back in. We're going to use it to monitor things. We're going to use it to loop back power. This is how I had it plotted before, and it looked great. Like, this should look great, not just good. That's better, but like, what the heck? Alright, let's try that one more time. We gotta wait for it to come around. I wasn't noticing what this was seeing. Man, we nuked something in a real way. Oh wow, kilowatt meter's not even booting. It's too dirty. It's too dirty. But we saw all the switching signals. They looked good. I'm guessing that we're only driving line or neutral. Something like that. It's gotta be something like that. I really thought we could resurrect this. I really wanted to show you the... Well, I wanted to show you lots of things. Wanted to show you this thing up to 500 watts. Wanted to try to get it up to a kilowatt. Made the gate drive more aggressive, but it looks like this daughter card is damaged in a way that is... I don't know. I don't really know what to tell you. I looked at the gate drive waveforms and they looked right. I mean, they weren't the most aggressive, but then again, we were switching at 30 volts instead of 130. Kinda should look a little weird, you know? But, yes, we replaced the FETs that had died. Replaced the FETs that had died. The timings were correct. Output filter looks good. And yet, something just ain't right. Let's take a quick peek at our high voltage bus. Just looking for shorts. No shorts. Alright, so I've disconnected the scope from the circuit. I'm going to see if the kilowatt meter comes up. Nope. And as a final effort to test this thing, let's really just give her, let's hook it up to the batteries and see what happens. We'll see. We'll see. Yeah, nothing's catastrophically wrong. It just doesn't... She just doesn't go anymore. It's as simple as that. Oh, and it looks like we're applying some DC. Yee, we're applying some DC to the bus. That's not good. Oh, that's very not good. Well, sadly, we gotta pack up the shop, and I'm not gonna have time to work on this for quite a while. So, we're gonna need to park this episode here. We've got enough magnetics, we've got enough wire. We can build more of these daughter cards. We can build up another one and plop it in, because honestly, I'm not sure where the fault is, but you know, I'm sure if we build up a new inverter and we picked up where we left off, we could make some good progress. The battery module's got some scars, but stay tuned for the next video where we're gonna wrap up this project. Sorry we couldn't show you 500 watts. I had a steam kettle that we actually hooked up to the output of this thing, and it started getting hot. It was working, so it's pretty cool. We were pumping enough power out of this to run a couple computers for sure. That's awesome. Right, that is huge progress. Went from 150 watts on the old one. That was about our absolute maximum. It was really more like 75. This one could pump out 500 comfortably. Could have probably gotten that up to a kilowatt, but unfortunately was not in the cards for us today. But as always, hope you learned something, hope you enjoyed, and we will see you in the next one. Bye.